end after the lecture, and then we'll have a closing remark. So for those of you that are not able to join in, can watch us live on YouTube on Health-Edu. And and please, I would like to remind the rest of us to mute our mics so that we do not interrupt Dr. Daisy as she's giving us the lecture on vaccine. Remember to write your real names on your real names, and if anyone has a question, please write them down in the chat box so that the Dr. Daisy can be able to answer the questions later after the end of the course. Thank you so much. I think I will welcome Dr. Daisy right now to take us through the course. Thank you.
Hi, Alan, you need to allow me to share my slides. It says that I cannot share.
Okay.
Okay.
Can you share now? Is it possible
Yeah,
to share?
sure, it's fine. Yes, it's fine. Can you guys see my screen now?
Yes. Yeah.
Okay. Okay, good afternoon, everyone. My name is Daisy Umutoni, and I'm going to share a little bit of what I know about the COVID-19 vaccine. So I'll start. Oh, sorry, it's not moving. Okay, so the objectives of my presentation are mainly the immune system, just a refresher of how it works and how vaccines work, the types of COVID-19 vaccines that are currently available, and the intention of vaccination, and then what we can do for community sensitization. So just a refresher, I know that most people here are doctors, but maybe some are not. So I'm just going to do a short refresher. So mainly our blood has red blood cells, and then it also has white blood cells. And the ones that are involved in the immunity are the white blood cells. So for example, macrophages, these are white blood cells that they swallow up and digest germs, and plus dead or dying cells. And the macrophages leave behind the parts of these dead cells or invading germs called antigens. The body then identifies these antigens as dangerous, and then it stimulates what they call antibodies to attack those germs. So also there are B lymphocytes. So macrophages are what is known as the innate immunity because they don't need to be activated, and they are found in most like parts of our body, and they'll just attack foreign germs. But B lymphocytes need to be activated. B and T lymphocytes are part of what is called the adaptive immune system, and they need to be activated by what they call antigen presenting cells. These antigen presenting cells basically just pick up the pieces of the germs that have been digested and swallowed by macrophages. So the left behind pieces are the ones that are presented, and they activate the B and T lymphocytes. So the B lymphocytes produce antibodies that attack the antigens left behind by the macrophages. And the T lymphocytes are another type of defensive white blood cells. They attack the cells by producing what they call cytotoxic agents that will directly kill the invading germ. So this is just a visual of what I was talking about. So when you get infected, or this is specifically for viruses, because there are different lines of response that our immunity employs to bacteria, viruses, fungus, and uh, uh, other germs. So this is specific for viruses, where when the virus enters your body, the immediate response is by what they call a natural killer cell. So these cells will detect the entry of the viruses and produce interferons. These are like some molecules, and these will be toxic to the infecting, they will kill the cell that is infected with the germs. And then, as I mentioned before, the antigens that are left behind after this killing are the ones that are presented to the adaptive immune response, which is B cells and T cells. And the B cells will produce antibodies, which are like these Y-shaped little things that will be specific for that particular germ. So for each germ, the body produces specific antibodies. So these will neutralize the virus. And also, antigen presenting cells will also present the antigen to T cells. So T cells are of two types, but here they just show the CD8 positive. These are called cytotoxic cells, and they immediately they will release cytotoxic molecules which will destroy the invading germ. So these are like the response to viral infection that the body usually employs. So then, from what I just explained, when we are used to a particular type of infection in the environment, for example, flu, measles, chicken pox that have been around for some time, the body already has these antibodies that neutralize that germ. They're already existing in our body. So either through vaccines, for example, measles and chicken pox, people are vaccinated when they're young. So you are immune to these germs because your body has circulating antibodies. For flu also, I think in some countries they have flu vaccines that they renew every year. And so they have also protective antibodies. But when we have a new germ on the scene, like COVID-19, like SARS-CoV-2, which causes COVID-19, the body doesn't recognize it because it has never been exposed to it before. So we don't have an neutralizing antibody, this Y thing, to attack the germ. So we can easily get severe disease and even have complications like death. So how do vaccines work? So this is, again, what I was talking about. The first time the body encounters the germ, it will take several days to make and use all the germ fighting tools needed to get over the infection. After the infection, the immune system remembers what it learned about how to protect the body against that disease. The body keeps a few. So how does the body remember about the previous infection? It will keep a few T lymphocytes, which are called memory cells, and these will remain circulating in your blood, and these will go into action quickly when the body encounters the same germ again. So that is how the immunity will, as I mentioned, for like measles or flu, the immunity will quickly produce the neutralizing antibodies because of these memory cells that it kept from the first time infection. So how do vaccines then compare to like the natural immunity? So vaccines help to develop immunity by imitating an infection. So this type of infection, however, is almost never causes illness. So this means instead of you like being attacked by a first-time infection and getting a severe complication, like dying, vaccines they will make something that imitates the real infection, but they'll make sure it cannot cause serious disease, or it cannot even cause disease at all. But what it will do is actually teach your immune system about this particular germ, so that when the real thing comes, when you are exposed, for example, to someone with the COVID-19 infection, your body can quickly produce the neutralizing antibodies, the Y things that I talked about, and also the T lymphocytes that destroy the cell, the germ directly. So once the imitation infection goes away, the body is left with a supply. So the imitation infection is the vaccine they give you. And once it goes away, the body is left with a supply of the memory T lymphocytes, as well as B lymphocytes that will remember how to fight the disease in future. So this way they protect you from the real disease by giving you a mimic of the infection, but they make sure that it cannot harm you. So before I go on, I know that maybe most of us have seen this image of the SARS-CoV-2 virus many times, but I'll just review it quickly before I go ahead. So this is the basic structure of the SARS-CoV-2 virus, and it's made of different proteins. The famous one is the spike, which is the S protein. And because these spikes are like, when they're combined, they look like a crown. That's why it gets its name corona. But that's for all coronaviruses, like have the same structure at the top. So so after the spike, there is the membrane protein, which makes up. So here, of course, it's a schematic, but in real life, it's like a continuous thing, which will form a membrane. And then the envelope as well, which is outside the membrane. And then you have the genetic material, which is the RNA, the single-stranded RNA of the virus. And this here is complex with the nucleocapsid, which is just the cover that contains the RNA of the virus. And this is an enlarged schematic of the spike protein, which is the most important protein that has been used to make most vaccines. So that's why it's important. So it has like different subdivisions, subunits, and from the from the outside part is the S1 subunit, and it's made of the C-terminal domain and the N-terminal domain. These are terminologies that maybe doctors would understand and scientists, but basically it's like the protein, the amino acids are small units that make up proteins, and each amino acid usually has a C-terminal and an N-terminal. And so this is what they mean by the C-terminal domain and N-terminal domain. These together make the receptor binding domain. This receptor binding domain is the one that binds to receptors on specific cells in the body. And the receptor that the SARS-CoV-2 virus binds to is called an angiotensin converting enzyme 2 receptor, which is found mainly in the lungs, but also in other body parts like the kidneys, the brain. There's been reports of presence of the receptor also in the GI, like the intestinal tract. And I think there's more, they're still discovering more areas where the SC2 receptors are located, and that can explain the different symptoms that people get. So, and then the S2 this part of the spike protein has what they call the fusion peptide, and this is what actually enables the receptor, the spike to actually fuse with the receptor and then enter into your cells. So what are the vaccine platforms that exist? I mean, currently. So first of all, there are some vaccines that are inactivated viruses. So what they do to, so here I'm talking about like the different ingredients of different vaccine types. And some are inactivated or dead vaccines, dead viruses. And what they do to kill it is to actually destroy its genome, is to inactivate its genome, or they can do what they call like passaging in different cell lines. So in the laboratories, they will grow the virus in one batch of cells, and then they'll take a little bit of the viruses and pass them to another batch of cells, and then a third batch. So the more they keep growing them in many either human or animal cell lines, the virus becomes weak. So that's how they produce the inactivated virus. And then there is also viral vectors. This is another type of way they make the vaccine. And the viral vectors, they just get a shell of a virus. So it's just a shell and it cannot cause any harm. And then they will use it to either package an RNA of for example, the SARS-CoV-2 virus, or they will include like some parts of the spike protein, or they'll include different parts. They can put different parts of the virus. So they use this viral vector to just carry that subunit of the virus into your cells, your body, and allow the immunity to react. And then there are live attenuated viruses, which are not dead, but they are weak. So for example, they can modify like the DNA of the virus to make it too weak to cause severe disease, but still still alive, not dead. So this one is completely dead. This is live but weakened, and it will still cause a immune reaction in your body to cause your body to protect you. And usually because it's alive, it will cause a stronger immune reaction or protective effect compared to the inactivated virus. And then the DNA viruses. So DNA viruses, hello.
Hello, sorry, Dr. Daisy. I would request everyone to mute, please, because we are interrupting. Thank you. Wow, commenting.
So the DNA viruses, they will, so the DNA and RNA viruses are both genetic material they use of the virus. So they'll basically, they take the spike protein of the virus, and then they take its sequence, its genetic sequence, which can either be RNA or DNA. And the difference is that when it enters your cell, the DNA first needs to be changed to mRNA, which is called transcription. So it will take a little bit longer. And then from mRNA, the mRNA will tell your cell to produce the spike protein. You remember the S, the spike, and this is the one that will initiate or provoke your cells to produce an immune reaction, neutralizing antibodies against that spike protein. And then when the real infection, when you get infected by SARS-CoV-2, the neutralizing antibodies are already present, and they will they'll stop the virus from replicating and causing like disease. So the difference is that mRNA will directly, doesn't need to be changed to anything. It will directly be changed to protein, but DNA will first need to be changed to mRNA. Yeah, so that's the difference. Viral protein subunits are just like, as I mentioned, for example, they won't take like the whole virus, because for inactivated virus and live attenuated, they'll actually take the whole virus, either completely inactivate it or weaken it. But here they just take a subunit, as I mentioned, like the spike protein, or actually most vaccines are just taking the receptor binding domain, not even the whole S protein. This is because they found that when they use the whole S protein, it can cause formation of, it can activate formation of other antibodies that are not necessarily the ones that are only needed to neutralize the infection. And those excess antibodies can actually cause disease enhancement and complications. So they prefer to just take a little bit, like the receptor binding domain, instead of taking so many pieces that can cause other complications. So that is what the viral protein subunits are. And then you have virus-like particles. These are also almost like this one I mentioned. Yeah, so I won't go into that, because most of the present viruses are in these other domains that I mentioned. So again, how the vaccine, what will happen, the immunity, how the immunity will react to an infection is the virus will enter or the vaccine. So this is someone's being vaccinated, and this will prime the antigen presenting cells. These will take that antigen, like the spike or the receptor binding domain of the spike, and they'll present it to T cells. T cells, they're of two types. The cytotoxic, which means the ones that kill cells, which are CD8 positive cells, and CD4 plus, which are called helper cells, because they help B cells to produce antibodies. So anyway, then the antigen presenting cells will present the antigen to naive T cells, and then they will activate them to replicate and differentiate into the cytotoxic type and the helper type. The cytotoxic type will directly go and kill the germ, the invading germ, by producing different like mediators. And then the T helper type will help the B cells, prime them to produce plasma cells that will actually produce the neutralizing antibodies, the Y things, the Y-like shaped things. And then also it will produce the memory B cells, which are the ones that stay in your body and are alert until you actually get infected by something that looks like the vaccine, which would be the real virus. And then they'll quickly react compared to someone who didn't have who didn't get the vaccine. And then the quick reaction will prevent you from getting severely ill, or it will even prevent symptoms. You may get infected, but it will protect you from being symptomatic. So, sorry, sorry about this thing. I don't know how it came through, but so I'm going to talk about the four main types of the current COVID-19 vaccines. So I mentioned a little bit before, but this is just the text of the types of vaccines. So the whole vaccines are there are two main approaches to whole vaccines: live attenuated vaccines used as weakened form of the virus that can still replicate without causing illness. And then inactivated vaccines use viruses whose genetic material has been destroyed, so they cannot replicate, but can still trigger an immune response. And then we have protein subunits, as I mentioned, that use pieces of the pathogen, which are often fragments of the pathogen is the germ, which are often fragments of the protein to trigger an immune response. Doing so minimizes the risk of side effects, but it also means the immune response may be weaker. So as I mentioned, the fragments, they'll take like this domain instead of the whole of it, and doing so will minimize risk of side effects, but it means that your immune response may be weaker because you have a smaller entity to trigger your immune reaction. And then we have nucleic acid, as I mentioned. They use genetic material, either RNA or DNA, to provide cells with instructions to make the antigen. So in the case of COVID-19, it's usually the viral spike protein. As I mentioned, it's like the golden part of the virus that all the vaccines are using. And once this genetic material gets into human cells, it uses our cells' protein factories to make the antigen that will trigger an immune response. Viral vector that I also talked about, they work by giving cells genetic instructions to produce antigens, but they differ from nucleic acid vaccines in that they use a harmless virus, different from the one the vaccine is targeting, to deliver these instructions into the cell. One type of virus that has often been used as a vector is adenovirus, which causes the common cold. So this is this one that I mentioned, like this will be like a shell, just a harmless part of, for example, the adenovirus that causes the common cold. And they're only using it because it has like some parts on its top that will make it easier for the genetic material that they're actually delivering to enter the cell and produce like produce like tell your cell to produce like the spike protein, which will go ahead to induce an immune reaction. So yeah, that's what this talks about. So what are the leading vaccines? So I got this from the New York Times page, which was updated yesterday. And these are the lists of the leading vaccines so far. I think there are other vaccines that are now also coming up, but these are the leading ones. And so there's the Pfizer BioNTech. So I put the red stars at the vaccines that I heard that Rwanda is going to import. So there's Pfizer BioNTech, which is an mRNA vaccine, as we saw. And then Moderna is, I'm not sure if we're going to import this one, but Moderna was made by the US, and Pfizer and BioNTech. Pfizer is a US company. BioNTech is a German company, so it's a collaboration. And then the AstraZeneca one, Oxford AstraZeneca, is also one that I think we're going to import in the latter half of this month. So I'm going to talk a little bit about these three types. So the vaccines that we receive in Rwanda, I'm going to start with BNT162b2 mRNA COVID-19 vaccine. This is the Pfizer BioNTech vaccine. So yeah, it's produced by Pfizer, so a Germany company, and BioNTech based in Germany and Pfizer based in the US. So this information is about the phase 3 trials that were done before the vaccines were kind of rolled out. So just a small explanation. So when they produce a medicine or any vaccine, they will first do what they call preclinical studies, which means they are studying how efficient it is, and its side effects and everything, but they'll do it in animal models. And then once it passes that, they'll go into phase 1 trials where they now start slowly introducing it into humans. So phase one, they just check, they try to check for side effects, and they try to check for the dose, the proper dose of whether it's a vaccine or a medicine, and they'll give it very carefully, and they'll start with smaller doses, keep increasing. If there's like severe side effects, they'll just abort the whole thing. So this is how they prepare these things before they can put them on the market. And then in phase three, so phase one and two, they just check for side effects and they try to confirm the dose. And then phase three is where they check the efficacy. Now, how good is this treatment or the vaccine? Is it working? And in this phase three, they make sure the participants are as many as possible in different parts of the countries of the world. So because but that depends on the target population. But for the COVID-19 vaccine, of course, it's for the entire world. So most studies include all races and as much as they can, and different regions of the world. So those are phase three trials. And once the drug passes that and the authorities okay it, then it can be put on the market. So the information I'm giving here is going to be about the results of phase three trials, which were the last in human parts of the studies before they actually put the vaccine out there. So this so for the BNT 162b2 mRNA COVID-19 vaccine, it's an mRNA vaccine. I mentioned who produced it. So they used a 2-dose regimen. They gave a 2-dose regimen in the phase three trials, and then it conferred 95% protection. It means 95% of the people that were included were protected against COVID-19. And it was done, the trials were done in people 16 years of age and older. So 95% protection, it means that they check, the people that were enrolled were not COVID, they had no infection, and then they let them continue to be in the areas where they live and where they could be exposed. And then they compare those who were given the vaccine and people who were given placebo. For this case, the placebo was just normal saline, which is sodium chloride in a solution. So which is to check compared to those who are given the vaccine, and they found 95% people, it prevented COVID-19 disease, as symptomatic disease, not asymptomatic, in 95% of these people. So the safety over a median of 2 months was similar to that of other previous vaccines made for other viruses. The safety profile of this vaccine is characterized by short-term mild to moderate pain at the injection site, fatigue and headache. The incidence of serious adverse events was low and was similar in the vaccine and placebo groups. So there were few side effects, and most of them were mild to moderate, like pain at the muscle of the arm, the upper arm, where they injected, and the serious ones were like fatigue and headache. Although there was a mention of a few people who got something called oh, sorry, I'm forgetting it. I'll mention it later. But it's a neurological condition where half of the face is kind of paralyzed, but it was very temporarily, and it was in a very small percentage of the people. So uh, it didn't rule out the success of the vaccine. So although another problem is that although the vaccine can be stored for up to 5 days, at standard refrigerator temperatures. Once ready for use, very cold temperatures are required for shipping and longer storage. So for countries like us who are very far and we need shipping and longer storage, it's still a problem, but they're still working on how to improve this vaccine to make it more amenable to normal temperatures for storage and shipping. So the second one, which is the second we're going to get in Rwanda, is made by Oxford, University of Oxford, and another company in the UK called AstraZeneca, and it's called CHAdOx1 nCoV-19. It consists of a replication deficient chimpanzee adenoviral vector. Sorry, I'll repeat that. So it consists of a replication deficient chimpanzee adenoviral vector, CHAdOx1. So remember I said vectors are like just shells that they use to carry what they want, the proper vaccine component. So this shell, which is CHAdOx1, contains the SARS-CoV-2 structural surface glycoprotein antigen, which is a long explanation to say the spike protein, the ACE. And so this shell, the CHAdOx, is from the chimpanzee adenovirus, and they just insert the S protein, and the shell helps the S protein to enter into the cells and cause your immune cells to react to this spike protein. And then, so it's not an mRNA, it doesn't use DNA material or RNA material. It uses the real spike protein, and this will cause like your immunity to react and make those memory cells that will remain and produce the proper antibodies to neutralize the virus if you get infected. So majority of the participants in this trial were 18 to 55 years of age. The participants in participants who received 2 standard doses, vaccine efficacy was 62.1% in that match in the vaccinated group versus 71% of this many people in the control group. And in participants who received a low dose followed by standard dose, efficacy was 90%. Overall efficacy across both groups was 70.4%. So in this study, they had 2 groups, and one group, so actually this study was done in South Africa. They used people from South Africa, Brazil, and the UK. And for these people, they had 2 groups. So for the UK people, I'm not yet sure why they used the first dose of the vaccine they gave the vaccinated group was a low dose, not the standard dose. And then later they were given the standard dose as the second dose. And then in the rest of the people, Brazil and South Africa, they were given standard dose for both the first dose and the second dose of the vaccine. So this is what they're talking about, that the efficacy was 62.1% in vaccinated people versus 71% in control group in participants who received a low dose followed by standard dose. So these are the UK people. Sorry. It's a bit confusing, but the point is that there were 2 groups, as I mentioned, and the UK group received a lower dose for first dose of the vaccine and a standard dose for second dose. And the other people, Brazil and South Africa, received standard dose for both first dose and second dose. And for all these two arms of the trial, they still found the overall vaccine efficacy across both groups was 70.4%. So that is a good percentage. They say that the reason why they use lower dose for the UK people is to see if they can still get the same result as those given the normal dose with less resources. So it means that they can increase like the efficiency of the whole process with even lower doses. So that was like one of the explanations for doing that. And then they found they had some few side effects, and some of the severe side effects were 3 cases of transverse myelitis, which is inflammation of a part of the spinal cord that will cause like some nerve-related symptoms. These were initially reported as suspected unexpected serious adverse reactions. Only one case, because after these people reported these side effects, then they appointed a group to actually study if it's really related to the vaccine, and only one case was suspected to be related to the vaccine. So you can imagine in how many thousands of people who were studied, only this one case was suspected to have a serious side effect. And the vaccine can be stored and distributed at 2 to 8 degrees, making it particularly suitable for global distribution. So this is like a better, more amenable to shipping and to faraway countries like Rwanda compared to the one for Pfizer. Sorry, it's stuck. And then, so Moderna, I don't think we're receiving this one for now, but I just wanted to talk about it because it's one of the ones that are like top in the world. So it's an mRNA, it's also an mRNA vaccine like the Pfizer one. It's called mRNA 1273 vaccine, and it's a lipid nanoparticle encapsulated mRNA-based vaccine that encodes the perfusion stabilized full-length spike protein of the SARS-CoV-2 virus. So this just means that they take the mRNA of the virus and they just put it in this nanoparticle, and the mRNA will tell your cells the factories in your cells to produce the spike protein of the SARS-CoV-2 virus. So it's produced in the US, and participants in the trial, phase 3 trial, were 18 years of age or older. Persons at high risk for SARS-CoV-2 infection or its complications were randomly assigned to a 1-to-1 ratio to receive 2 doses of the vaccine, which was each was 100 micrograms, or placebo, which is the control group. And these doses were given 28 days apart. And they found that the vaccine efficacy was 94.1%, means that it protected symptomatic disease in 94.1% of these people. So Moderna was only tried in the US population, and it mainly the trial was done mainly on white ethnicity, white race. So they had a few other like minority ethnicities, and I think that's one of the limitations for now. And overall local reactions, so still on the Moderna vaccine, local reactions to vaccines were mild, however, moderate to severe systemic side effects such as fatigue, myalgia, which is pain, muscle pain, arthralgia, joint pain, and headache were noted in 50% of participants. in the vaccinated group after the second dose. So these side effects, however, were transient. They didn't last, and they started about 15 hours after vaccination and resolved in most participants by the second day without like long-term complications. So the general limitations of all these current vaccines is that they have not yet found evidence that they prevent asymptomatic disease and transmissibility. It means that they don't know whether, like they know that the vaccines, they have proof the vaccines can protect you from disease, but they don't know if it can protect you from carrying the infection without having the disease, or if it can stop you from passing on the infection. And the duration of vaccine protection has not yet been confirmed beyond 2 months. So this making of vaccines has been like a marathon. It usually takes around 5 or more years to make a proper vaccine. But because of the situation of the pandemic, they had to do a marathon to produce these vaccines within a year. So most of them were produced on average within 11 months. So this is why the follow-up after giving people vaccines hasn't gone beyond 2 months for most vaccines. So that's a limitation. But for most vaccines, they didn't stop the trials. They're actually still following up those people in longitudinal studies, and they want to see the long-term protection that the vaccines can provide, and all these other things like whether it can protect you from just having the asymptomatic disease or transmission. And also the limitation that most of them also had is they didn't study children below 15 years of age. They didn't study specifically pregnant women, although the vaccine is not contraindicated in pregnant women, but they didn't specifically study them to see if they have spatial things they need to consider. Also for Moderna, as I mentioned, there are some problems with like the population they studied had less diversity in terms of race and ethnicities. They also still need to study dose regimens for different subgroups, like to do finer studies, and also timing of booster vaccines. So boosters are like, another dose that they give you later on to just make your immunity produce even more antibodies. So they need to study when they should do these booster doses. But given like the collaboration of the world, different organizations and different researchers and the resources they put in, I think for now, the vaccines are safe, but they still need to do longitudinal studies for longer, like how long this protection is gonna last. They still don't know, as I mentioned, and also for children, because up to now, only children 16 years and older can actually be given the vaccine. So, yeah. So what is the intention of vaccination? So basically it's just to increase immunity against the vaccine and preventing severe disease and reducing the ongoing crisis. And this can be achieved through what they call herd immunity. This is also known as population immunity, and it's the indirect protection from an infectious disease that happens when a population is immune, either through vaccination or immunity developed through previous infection. So yeah, as I mentioned, the natural infection will also give you immunity. The vaccine will also give you immunity. But the WHO supports achieving this community or herd immunity through, population or herd immunity through vaccination, not by allowing a disease to spread through any segments of the population, as this would result in unnecessary cases and disease. So this is because some people say, why can't they allow the infection to just spread until everyone gets immune? But some people, this will lead to a high human cost because, you know, so many deaths have occurred, especially in some countries, and some people, some reports of even later complications in people who were even who got asymptomatic disease are still, being documented. So it would cause serious damage to human lives and also the economy eventually if we just try to achieve immunity through natural infection. So that's why vaccines are important. So one of the aims with working towards herd immunity is to keep vulnerable groups who cannot get vaccinated, for example, due to health conditions like allergic reactions. Also people with low immunity like HIV patients or cancer patients or other immunocompromising conditions cannot be given these vaccines. So the point of herd immunity is for everyone who can be vaccinated to be vaccinated in a certain population. And if you have many people vaccinated and immune, these people are enough to stop the virus from jumping around to the next person. And this will end up protecting even the people who cannot be vaccinated. So this is the whole point of herd immunity. So the percentage of people who need to be immune in order to achieve herd immunity varies with each disease. In the case of COVID-19, 60 to 70% immunity in a given population is needed. So for community sensitization, what you could say to people or you could tell yourself is that you can actually help to stop the pandemic by getting a COVID-19 vaccine. We need to use all our prevention tools. Vaccines are one of the most effective tools to protect your health and prevent the disease. And then COVID-19 vaccines are safe and effective. So vaccine safety systems that make sure that all vaccines are as safe as possible exist in those countries where these vaccines are being made. For example, the FDA in the US, they really do a lot of rigorous checks to really make sure these vaccines are as safe as possible. And if you want to read more about what the US is, how the US is working to ensure this, you can Google it on safety of COVID-19 vaccines. I'm sure they will share this presentation so you can get this information. And then you still need to wear a mask and socially distance after getting each shot of the vaccine for now. As experts learn more about how COVID-19 vaccination may help reduce spread of the disease, the CDC will continue to use the latest science to update the recommendations for protecting communities. So as I said, they still don't know if you can not get infected when you get the vaccine. It will protect you from getting symptoms, but they don't know yet. They're still trying to study it. They don't know yet if it will stop you from carrying the virus or passing it on. This is the reason why you still need to follow those infection prevention and control measures that we already have in place, like wearing masks, washing your hands, social distancing, and all those things. So the bottom line is that vaccines, like any medication, can cause side effects. The most common side effects are mild. However, many vaccine preventable disease symptoms can be serious or even deadly. Even with advances in healthcare, the diseases that vaccine prevent can still be very serious, and vaccination is the best way to prevent them. So My presentation is done. Um, Back to you, Annette.
All right. Thank you so much, Dr. Daisy. This has been a very, very good and very, very educative lecture for us,
Thank
most
you.
us that are not in the industry. We've really been able to learn a lot. We have quite a number of questions here, and please keep sending in your questions so that Dr. Daisy can answer them. For the other doctors that would like to make additions on the answers and questions, I would request you to put up your hand so that we'll be able to see it and then give you a chance to put in additions. So if Dr. Daisy, if you're able to see the questions, I think I'll give you back
I
the.
actually have not seen them.
Okay,
Um,
so um, I'll read. I'll
oh,
read for
okay.
you.
I do see them. I do see them.
Okay.
So I'll read the questions. Do people still have to wear a mask after getting the first dose, second dose? I think I talked about this just before I finished, that because they still don't know if the vaccines that are currently available can prevent infection, even though they know that they can prevent the disease, the symptoms, but they don't know if they can stop the infection from entering your body, and whether they can stop that infection from spreading to others. So because they still don't know yet, we still need to wear masks and wash our hands and uh, stay 1 meter or 2 meters away from people. So yeah. The next question is the face mask causing headaches. I really don't know. I cannot answer this question. Maybe someone else can help me to answer this. At the end of the presentation, I need to know among the group to be vaccinated, are pregnant, lactating women vaccinated? What about young age children? So as I mentioned, there is no contraindication so far to pregnant women or lactating women. They can be vaccinated. Of course, the doctors have to monitor everything, but there is no contraindication. And for children, I mentioned for now, the vaccines are available are for children above 16 and, people from 16 years of age and above. Now they are continuing studies, and they are going to study all these things like specific subgroups, younger children. There is now I think the Pfizer and BioNTech collabo has started studying children now between 12 and 15, and they will continue to lower the age with time. And also they're also studying pregnant women and other subgroups. But for pregnant women, there is no contraindication. They're just going to study them more than they have studied them. Are the videos circulating that once you are given the dose, you turn to a zombie or black out? True. Okay, of course not. I haven't seen the video, but no, of course not. Like, as I mentioned in the trials of these current vaccines, there hasn't been such a thing like turning into a zombie or anything like that. It's not true, and you can read a little bit more for yourself. So thank you. Someone reminded me Bell's palsy. Yeah, that's the side effect that I forgot during the presentation, where half of the face becomes paralyzed. And this was detected for the Pfizer and the Moderna vaccines. And they found that this was very temporary side effects. But of course, they're still going to study, try to make some changes in the vaccine composition. But yes, that's Bell's palsy. Thank you. Um, if the vaccine allows to prevent symptomatic disease, does it mean that those getting the vaccine can still be infectious if they acquire the disease? Do they acquire the disease? So I mentioned again, they only found that they protect from symptomatic disease. So you don't acquire the disease, but they still don't know if you, so acquiring the disease meaning getting sick, getting symptoms, but you could still carry the virus. They're still not sure. You could still get infected, but not get sick. And during that time that you're infected, if you could get infected, you can pass it on to other people. They're not sure if that will happen or not. So as I said, they're still studying that. But the result they have now is that it will prevent it will prevent symptoms. So it will prevent disease. It will prevent disease. Sorry. COVID-19. Are there any promising suggestion for interim medications while a vaccine is developed? So I haven't read much into this, but I think there are so many medications that are out there, but they don't cure. I think they just, they just ease symptoms like the remdesivir and others that have been put out there. I don't think they found a cure yet. So for now, I don't think there is a treatment, but I'm sure they're really studying that. Based on her explanation, is Bell's palsy syndrome? Yes, thank you. Is this efficacy of 70 sufficient? I think it's sufficient because, as I mentioned, for example, if you look at herd immunity, you need like 60 to 70%. So if you have like a population and you can get 70% of people uh, immune, then I think that's pretty much sufficient, because actually it's not only for COVID-19 vaccines. I think there is no vaccine that is 100% efficient of all vaccines that have been made up to date. So this is, I think, is efficient, and I think they are going to try to improve these vaccines, and hopefully we get higher efficacies. I got some information from newspapers in Australia that they stopped vaccinating their people as they developed some signs of HIV/AIDS. Are these vaccines well checked and effective, or it's countries' competition? So I think different countries have different vaccines in their pipelines and those that are already out there. The Australian vaccine is true, it was stopped, and from to what I know now, is that it caused a false positive. It did not give people true HIV, but it caused false positive in a small number of the people that were in the trial. And because of that, they stopped it, but it was not a true positive. Something about the vaccine mimicking the HIV virus in a way that caused a false positive. Um, I'm not so well versed with how that happens, but what I know is that there were false positives. Those people didn't actually get HIV, and that only happened in Australia, and they stopped that trial immediately. And yeah, so it's not all vaccines that gave people HIV. It was just the Australian one, and it didn't give them HIV. It was a false positive, and because there are all these people observing and studying and watching the people, they stopped. The people didn't get any symptom, just the blood tests gave false positives, and they stopped the vaccine. So I wouldn't say that, these people are just lying to us and competitions between countries. Ultimately, I think they're doing a good job, and they're watching, all these things closely for any side effects. I would like to know if after vaccine, the person who was vaccinated has headache, and fatigue, and we know that it was also the one of signs of COVID. It means that the vaccinated person still have an infection. No, I think these people, they before they went into the trials, they make sure they were not COVID-19 positive. So for most vaccines, that's how they studied to make sure that actually they're protecting against the infection itself. And these signs that happen is because, as I mentioned, a vaccine is a mimic of the real infection. So when they mimic the real infection, your body will react, will give an immune reaction. And the immune reaction is the one that produces, in some people, not all of them, some symptoms like fever, fatigue, headache. So the immunity is like reacting to that fake infection, which is the vaccine, but it's not the real infection. Those people are not infected with COVID-19. I hope I answered the question. So another person says, my question is why WHO is not approving the Chinese and Russian vaccines? No political reasons behind, I don't know. I really don't know. I cannot comment on the political part. Yeah, I think with the knowledge we have, maybe we should look into it further. But I do not think personally that it's political reasons. I think the WHO is being fair to all producers of vaccines, and probably um, there's some rules they didn't adhere to, or some things that are causing their vaccines not to be approved. I remember reading about the Russian vaccine be like they jumped some steps in the clinical trials, and they even before they concluded the phase 2 trials, they were already vaccinating people. So these are some of the reasons the WHO block didn't approve these vaccines to go to maybe other countries other than Russia and China. What is the explanation of the high efficacy of the AstraZeneca vaccine when using a lower first dose? I think they have not done the mechanistic studies to understand why the lower first dose group has a high efficacy. Actually, it doesn't have a higher efficacy than the other group that got both standard doses. It's just they had the same efficacy. So then they said, oh, if we can have one group with a lower dose have the same efficacy as that had a high dose, then probably in future we can use less resources and get the same result. But they haven't studied the mechanism of why the response was equal. So I hope I answered that. Oxford AstraZeneca, the one which is a vector-based heterogeneous, they did third trial in Russia. The efficacy was 91.6% efficacy against COVID-19 and was well tolerated in a large cohort. That's very good news. Thank you. I didn't know that. I'm reading in a newspaper that in the USA, there are people who are being tested positive after getting a vaccine. What might be the cause? So I think for these studies, sorry, there's an echo, I don't know why. I think for most of these studies, if you read all the papers, there is always a small percentage of people that don't respond very well, but that's why they use percentages. So in all these studies that I checked, there were small percentages of people that really did indeed get COVID-19 during the trial, even when they were given the vaccine. But that was like a very small percentage compared to like maybe 90% who didn't get any symptoms. So that cannot stop a vaccine from being used, especially in the emergency situation that we're still in. And if you're asking why that is happening, I don't know. That's why I say this, they didn't stop these studies. They're all still ongoing, and it's like fine tuning them and understanding further. So maybe the media will just take that part of the study and amplify it, but it doesn't give all the details for you to actually decide whether the vaccines are efficient or not. So it's true, some people do get the disease, but that's a very small percentage of the studied population.
Hello?
Can you hear me?
Dr. Daisy?
Yes.
There was noise in the background. Do you think we could take like 2 minutes for a break? I feel like you need to catch a breath. There are so many
Yes.
questions,
Thank you.
and yeah,
Thank you.
yeah. So keep your questions incoming for those of you that have questions, and we could also as well thank Dr. Daisy for the good lecture and questions answered. I think we will get like a 2 minute break and then come back after. Yeah, thank you. All right. So,
Hello.
yeah, so there's a sound problem at your end.
Oh, you can hear me?
We can. It's now okay. So thank you everyone
Okay.
Yes.
for the break, and I hope Dr. Daisy has taken some water. We are now back to the questions, and she was going to answer all your questions. Thank you so much. You are on mute, Dr. Daisy.
Okay, sorry. You hear me now?
Yeah, yeah.
Okay, I'll keep reading the questions. Um, so someone asked, I heard that some women recovered from COVID-19, who recovered from COVID-19 got a complication of losing their hair and men losing their sexual desire. If yes, does the vaccine will the vaccine work on the complications, or are there any medications to be used to prevent those complications? Um, so I don't know all the complications that are currently present of COVID-19 because it's a whole new disease and virus, and I think nobody knows everything about it. But I think vaccines so far, as I mentioned, they've studied prevention of disease. So if they prevent the disease, then definitely they'll prevent those complications from happening. But whether the vaccine, I don't know whether they have medications. Of course, in normal, I think clinical, I mean, in normal medicine, they have medicine for these things like loss of hair or loss of sexual desire. So I think for people who have COVID-19 and get those complications, they will be treated just the way people who get such conditions from other illnesses will be like treated. There are medications for those things, even if it's not caused by COVID-19. But as far as the vaccine is concerned, the vaccine, if it stops you from getting disease, it will stop you from getting like complications. But of course, they're going to study these things as well. They're long-term complications. Thanks for a good presentation. Now relating to Moderna, if prevention of asymptomatic disease and transmissibility is not yet known, its protection is not yet confirmed, why would they put such a vaccine on the market? So I think even if they cannot yet confirm asymptomatic infection or transmissibility, they are preventing severe disease. They're preventing any symptoms and also disease with symptoms and also serious complications, which we have had. The worst of all is death, of course, but there are other heart conditions, neurological conditions, and other like severe complications. So if they can introduce a vaccine that can prevent severe disease, I don't think that's a waste of resources. And I don't think we have the luxury to not use it now because we don't know if it's preventing asymptomatic infection. If we can reduce the number of deaths, then we can even, uplift restrictions, and the economy, the economies of the world will be revived if people are not dying or having severe disease, and maybe the asymptomatic infections are not yet prevented, but then at least some part of normal life will be revived. So I think that's worth it. And that's why the vaccines still should be used at this point. So I heard that in the UK, they discovered a second mutation of COVID-19. Will those vaccine be sufficient? So I think the question is, are the current vaccines going to target the mutation that was discovered in the UK? So from what I have heard from WHO is that so far the UK, fortunately, the UK mutation is still targeted by the current vaccines because they found that, so actually viruses keep mutating and not all, like most mutations are deadly to the virus. And a few mutations will actually give like an advantage to the virus to be more infectious or something else, or to survive a certain drug or something. But it doesn't mean that every mutation will cause the virus to not be targeted by the current vaccine. So the variant that was found in the UK and I think in South Africa as well was in the variation was in the genetic sequence of the spike protein. But when they did some studies using the current vaccine, they found that nothing had changed. The vaccines can still target the variant in the UK and in the US. So I think the only one that they actually have not yet confirmed is the one in Brazil, which is also another variant. And of course, they are racing against the clock to check if the current vaccines can target that one as well. So the questions I have here, those are the questions I have so far. So I don't know if Alan has other questions.
Yeah, there's one in the chat about do people who have recovered from COVID-19 need to take the vaccine for it again?
So I'm not so sure about that, but one thing is that they still need to do serological tests, which are like like measuring the antibodies. This is something else that also hasn't been very confirmed, because there's been reports of possible reinfection in people who were infected before. So I think in order to answer that, I can say that the researchers are trying to check the antibodies using serological tests to see, to study and see if these antibodies are actually enough to protect an individual, the ones that are produced by the first infection. So there is no, I don't think there's evidence yet that these people cannot be infected again if the natural protection is enough from the first COVID-19 infection. So I would say that these people still need to be vaccinated if they're in the proper age group and they don't have other contraindications like being severely immunocompromised. Yeah, I would say that they still need to be vaccinated unless we come up with the tests that are necessary to check the, I mean, unless they confirm that the antibodies are produced by the natural infection are enough to protect someone, which has not yet been confirmed. So
All
yeah.
right. Okay, so thank you so much. I see a hand up by Tuishime Pierre. If you could unmute and ask or an addition, you're welcome.
Okay. Uh,
Sorry, Pierre, you are on mute. Okay.
let's
There is the background noise. So it's not easy to. Do we have someone else? Okay, let's try again with Pierre and see if we can
Yeah.
Hello?
Oh,
Hello
okay.
there. Okay. I think he has. Yeah. As we're waiting for Tuishime, there was a question here. What can be a take-home message about the vaccine? About the vaccine.
Um, I think the take home is like, as I mentioned in the bottom line of my presentation, is that of course the vaccines, like they don't have all the answers yet, but you know, there are some few side effects, some that have even been severe, but in very small populations who were studied, small parts of the population. So overall, I think the current vaccines are safe enough um, to be used to prevent disease and especially serious complications. And for that, they're worth being used in order to alleviate the current crisis on, you know, the cost of human lives, the economy, and all other things. So I think the vaccines are some of the best tools we have in our toolbox at the moment. But of course, also the public health infection prevention control guidelines will continue to be used until they actually keep studying these vaccines and do more trials and get more answers to be able to use in young people, like younger kids and all the other subgroups, until they know that infectivity also can be, sorry, um, until they know that they can prevent the infection at all, and then they can prevent transmissibility. All those answers will come in time, but for now, I think the vaccine is good is justified to prevent the serious complications and to return us to some kind of new normal, as we continue to also use the public health advice that was already going on. So I think that's what I can say about the vaccine, the take-home message.
Okay. Yeah. Thank you so much. Another question is, will those people to get vaccine first get tested for COVID because you may be with it while no symptoms? What would you advise?
They get tested. I think in most studies, I saw a little bit about a study where they actually had a small population of people who they knew they had already COVID, and I think they were studying something else. But for most of these vaccines, the people who are enrolled are either the control group or those who receive the vaccines. They do the RNA test, the RNA PCR tests, and they make sure that they are not infected. So they're exposed later after getting the vaccine, meaning that they allow them to, you know, keep living their normal lives. And then they will study those who get like symptoms and all that stuff. So yeah.
Okay, so another question is, does the route of administration of the vaccine affect its efficacy?
Um, No, I don't think so. It has not been mentioned so far. So far, the route that I know of is the deltoid muscle. It's on the upper arm, and it has caused some complications like pain, some very mild, some moderate, a few people severe. Um, but efficacy, I'm not sure. It has not been documented so far, so I cannot say much about whether there could be improved efficacy if they use another route. But Yeah, so far there is no documentation of the efficacy being affected by that route that they're using at the moment.
All right. I have no questions so far from the chat. I think they're done. I would like to extend my appreciation to Dr. Daisy. Thank you so much for the presentation. It was excellent, and the lecture, it was nice. We really learned a lot from this. Thank you for your time, and also thanking the participants that were able to ask and mute and follow with us from the beginning. Yeah, thank you so much.
Thank you everyone for listening. Yeah, thank you.
Yeah, thank you so much. So I would like to welcome Mr. Jean to give us closing remarks. Yeah.
Thank you very much, Alan. Thank you very much, and thank you very much, Dr. Daisy, for a good presentation. I'm very happy that we are at the end of these sessions. Yeah, and let me take the opportunity as well on behalf of RHF to thank all the presenters from Dr. Leonce, Dr. Anita, Dr. Jimmy, Dr. Mugabe, and Dr. Daisy, who has just presented. And let me hope that we learned a lot throughout this process. And this is from the support from the African Economic Research Consortium through Rwanda Healthcare Federation. So we have noticed that a big number of professionals are willing to learn, and they participated. We got a lot of people who have joined on YouTube, yeah, and some here. So we're going to keep on organizing such events so that we can learn and then try to improve together. We will share the course materials to everybody. And for those who participated for more than 50% of the event, they will receive a certificate of completion. Yeah, that's it for now. Thank you very much. And then see you next time.
Thank you, everyone. See you next time.
Murakoze cyane.
Thank you so much for so amazing.
Murakoze.
Uzangaroto. Sira.
Thank you, everyone. You can find the presentations on the Health-Edu platform and the recordings. You can also access email, the one that has been sending you reminders for any more questions that you may have. Thank you, everyone. See you next time. You can log out. Thanks.